Welcome back. Let's practice using the cross product. All right, so here's our first example. We want to find the cross product of vector v and vector u if vector v is equal to 3i plus 4j plus 5k and vector u is equal to 6i plus 7j plus 8k. All right, and so the way that I recommend that we go about this problem to calculate the cross product between two vectors is to use the determinant form of the cross product. And essentially what that involves is setting up a 3x3 matrix using the components of our vectors and then calculating the determinant of that matrix. And so here's what that looks like. We're going to have vector v cross vector u is equal to a 3x3 matrix where the first row is just going to be our standard unit vectors. So that would be I, j, and k. All right, and then the next two rows are going to be composed of the components from vector v and vector u. Since we have vector v cross vector u, vector v comes first, the components of vector v will be in the second row, and the components of vector u will be in the third row. Now the components of these vectors will be the coefficients of I, j, and k. So the components of vector v are 3, 4, and 5, and the components of vector u are 6, 7, and 8. So let's write those into our matrix here. We're going to have 3, 4, and 5, and then 6, 7, 8. Okay, those are the components of vector v, and these are the components of vector u. Now, what we want to do is calculate the determinant of this matrix. And to calculate a 3x3 determinant, what you have to do is look at the values in the top row and work with each of these one by one, multiplying them by a 2x2 matrix, or the determinant of a 2x2 matrix. And so let me show you what I mean by that. Let's start with vector I. That's the first value in this first row here. What we want to do is temporarily cover up or cross out the row and the column that vector I is located in, and then the remaining four values are going to make up the 2x2 matrix that we will then calculate the determinant of, which will be multiplied by vector I. All right, so here's what that will look like. We're going to have a 2x2 matrix involving those four values that we were just looking at. So we're going to have 4 and 5 and 7 and 8, and that is going to be multiplied by vector I. Okay, and so what we're going to end up doing is taking the determinant of this 2x2 matrix, and that will be multiplied by vector I, which will be the x component of the vector that results from the cross product of these two vectors. All right, so that's the first part of it. Then we're going to have another term, but we're going to subtract it. You always subtract the second term, or the matrix that you're going to be multiplying by vector j. That's where we're headed next. We did vector I, now let's move on to vector j. To see what values from this matrix we're going to use for a 2x2 matrix to multiply by vector j, we're going to temporarily cover up or cross out the row and the column that vector j is in, and the remaining four values will make up our matrix. So we're going to have 3, 5, 6, and 8. All right, so let's write that in here. We'll have 3, 5, 6, and 8, and that will be multiplied by vector j. And then we have one more term. We're going to be adding this one, and that will be another 2x2 matrix, or 2x2 determinant that we're going to calculate, which will be multiplied by vector k. That's our last value in this first row. Okay, in particular, if we temporarily cross out the row and the column that vector k is in, then we can see the remaining four values that will make up that matrix. So we're going to have 3, 4, 6, and 7. Okay, so here's our matrix. We're going to have 3, 4, 6, and 7, and that will be multiplied by vector k. All right, so this right here is going to allow us to find the cross product of vector v and vector u. Now what we have to do is calculate the determinant of each of these smaller 2x2 matrices. And that part's pretty simple. In order to calculate the determinant of a 2x2 matrix, what you do is you multiply the top left by the bottom right, and then subtract multiplying the top right by the bottom left. All right, so we're going to have 4 times 8 minus 5 times 7. So I'll write that out here. This is going to be equal to 4 times 8 minus 5 times 7. All right, and that will be multiplied by vector I. Then we're going to subtract the determinant of this matrix. So we're going to have 3 times 8 minus 5 times 6. So let's write that in here. We'll have 3 times 8 minus 5 times 6, and that is multiplied by vector j. And then we'll add that to the determinant of this matrix, which will be 3 times 7 minus 4 times 6. All right, so we'll have 3 times 7 minus 4 times 6. And that is all multiplied by vector k. All right, now if we simplify, 4 times 8 is 32. So this will be equal to 32 minus 5 times 7, which is 35. And that is still multiplied by vector I. Then we will subtract 3 times 8, which is 24. So we have 24 minus 5 times 6, which is 30. And that's multiplied by j. And then we're adding 3 times 7, which is 21. So we'll have 21 minus 4 times 6, which is 24. So we have 24 times k. All right, now if we simplify one more time, 32 minus 35 is negative 3. So this is equal to negative 3i. And then we're subtracting 24 minus 30 times j. 24 minus 30 is negative 6. And then we're going to be subtracting that, so that will become positive 6. So we'll have plus 6j. And then we're adding 21 minus 24 times k. 21 minus 24 is negative 3. So we will have minus 3k. And that right there is our final answer. It is the cross product of vector v and vector u. And in case you're wondering, what this represents is the vector that would be orthogonal or perpendicular to both vector v and vector u. That's what this vector represents. Okay, and so with that, that is how you find the cross product between two vectors. All you have to do is set up a 3x3 matrix like we did right here, and then calculate its determinant. All right, and in this example, I showed all of the individual steps here of drawing out these 2x2 matrices and then showing all of the calculations involved in finding the determinant of each of those 2x2 matrices. But for time's sake, with the rest of the examples in this video, I'm probably not going to show as many steps here. We'll do some of this multiplication in our heads so that we can cover a lot more examples. All right, but I wanted to show you all of the work at least one time so that you can see what we're doing. Okay, but with that, let's take a look at some more examples of finding the cross product of two vectors. Okay, so here's our next example. We want to find the following if vector A is equal to negative 2i plus 4j and vector B is equal to 3i plus 2j plus 5k. And we want to find the following three cross products. We want to find A cross B cross A, and A cross A. And so let's start with the first one here. Let's find A cross B. We want to start by creating a 3x3 matrix. So that will look something like this. We'll have vector I, vector j, and vector k in the first row, and then the second and third row will be the components of vector A and vector B. Since vector A is first, we'll have vector A's components in the second row, and then the third row will be vector B's components. And the components of vector A are negative 2, 4, and then 0. Right? Since there's no k term, we can just assume that the z component is 0. So we'll have negative 2, 4, and 0. And then for vector b, we have 3, 2, and 5. So I'll write 3, 2, and 5. Okay, now that we have that drawn out, let's calculate the determinant of this matrix. We'll start by looking at vector I here. We're going to be multiplying that by the determinant of a 2x2 matrix created by the leftover values after we cover up or cross out the row and the column that vector I is in. So we're going to be using these four values right here. All right, and so we're going to take the determinant of this 2x2 matrix. So we're going to be multiplying 4 by 5 and then subtracting 0 times 2. All right, and 4 times 5 is 20, and 0 times 2 is 0. So we have 20 minus 0, and that's multiplied by I. Okay, so that's the first part. Now let's move on to our next term. We're going to be subtracting this one. You always subtract that middle term where you're going to be multiplying by j. And this time we're going to be taking the determinant of the 2x2 matrix formed by the values left over after we cover up or cross out the row and the column that vector j is located in. So we're going to be working with these two values and these two values. All right, so we're going to be multiplying negative 2 by 5, and then subtracting 0 times 3. Okay, so negative 2 times 5 is negative 10. So we'll have negative 10 minus 0 times 3, which is 0. So we're subtracting 0 and then multiplying by j. All right, then finally, we're going to add that to one more determinant, but this time it will be multiplied by vector k. So if we go back to our 3 by 3 matrix here, we want to calculate the determinant of the 2 by 2 matrix formed by the values left over after covering up or crossing out the row and the column that vector k is located in. So now we're left with these 4 values right here. So we'll take the determinant of this 2 by 2 matrix here, formed by those 4 values, which means that we'll be multiplying negative 2 by 2 and then subtracting 4 times 3. And negative 2 times 2 is negative 4, and then we're subtracting 4 times 3, which is 12. Okay, so once again, negative 4 came from multiplying negative 2 times 2, and then we're subtracting 4 times 3, which is how we get minus 12. All right, now if we simplify, 20 minus 0 is 20. So this is equal to 20i minus negative 10 minus 0 times j. That's just going to be negative 10. So we have negative 10j, but we're subtracting it, so that will become plus 10j. And then finally, we have plus negative 4 minus 12 times k, and that will become negative 16k. So we will subtract 16k. All right, and that right there is the vector that results from the cross product of vector A and vector B. So now we found that vector. Now we want to find vector B cross vector A, the reverse of that, and you might think it would give you the same answer, but it actually doesn't. The cross product is not commutative. The order in which those vectors are placed does matter. A cross B will not be the same as B cross A. However, they will look very similar. And I'll explain that in just a second. In fact, if you watched my lesson video, you might already know what that vector will be. But in case you didn't, let's just go through the process of calculating the cross product again. Let's set up our 3 by 3 matrix. We'll have vector I, j, and k. And then the components of vector B will be in the second row since vector B is first. And then the components of vector A will be in the last row. Okay, so we'll have 3, 2, 5, and then negative 2, 4, 0. And so if we calculate the cross product here, we're going to have I multiplied by the determinant of this 2 by 2 matrix. So we'll have 2 times 0 minus 5 times 4. All right, so 2 times 0 is 0, and then subtracting 5 times 4, which is 20, and that will be multiplied by I. Then we're subtracting that middle term, where we're going to look at vector j, and so we'll have j multiplied by the determinant of the 2 by 2 matrix made by those 4 values. So we'll have 3 times 0 minus 5 times negative 2. 3 times 0 is 0. And then we're subtracting 5 times negative 2, which is negative 10. And that's multiplied by j. And then we're adding that to our last term where we have vector k. And so if we go to our matrix here, we're going to be taking the determinant of these 4 values here. So we'll have 3 times 4 minus 2 times negative 2, which will be 12 minus negative 4. All right. 3 times 4 is 12, and 2 times negative 2 is negative 4. Now, if we simplify, this will be equal to 0 minus 20 times I. That will be negative 20i, and then we're subtracting 0 minus negative 10 times j. 0 minus negative 10 will be the same as 0 plus 10. So we have positive 10j, but then we're subtracting it, so we have minus 10j, and then we're adding that to 12 minus negative 4k. 12 minus negative 4 is the same as 12 plus 4, and 12 plus 4 is 16, so we'll have 16k. And that right there is the vector that results from the cross product of vector B and vector A. Now, if you compare that to A cross B, you can see that the components are the same, except they are negated, right? We have positive 20, then negative 20, positive 10, then negative 10, negative 16, then positive 16. And so what we observe here is that when you reverse the order of the vectors in a cross product, you simply get the same vector, but it's negated. All 3 components have the opposite sign, which means that that vector would be pointed in the opposite direction as the other vector. Okay, and I talk about that in more detail in my lesson video. Once again, if you didn't watch it, be sure to watch that first. But in general, from here on out, if you're ever asked to find the cross product between two vectors and then the reverse of that, don't go through all of this work again. Just take that vector you already found and then negate each of those components. Okay, and then finally, we have one more cross product that we want to find. And once again, if you watched my lesson, this might be a fairly easy cross product to calculate because it has to do with one of the properties of the cross product. But if you're not sure what that is, don't worry. I'm going to show you what this results in, and it's pretty interesting. Let's set up our 3x3 matrix here. It's going to look like this. We'll have vector I, j, and k. And then our two rows of components are both going to be the components of vector A, since we have A cross A. All right, so we're going to have -2, 4, 0, -2, 4, 0. Now, if we calculate the cross product here, we're going to have I multiplied by the determinant of those four terms. So we're going to have 4 times 0 minus 0 times 4. That's just going to be 0, right? We're going to have 0 minus 0 times I. And then if we subtract the next term, we're looking at j. So we'll cross out this row and this column. We're going to be working with these four values. So we'll have -2 times 0 minus 0 times -2. Once again, both of those will be 0. So we'll have 0 minus 0. Right? It doesn't matter what you multiply by 0. The result will be 0. And that's multiplied by j. And then we have one more term for vector k. And so if we cross out the row and the column for vector k, we're working with these four values. -2 times 4 is -8, and then 4 times -2 is also -8. So we have -8 minus -8, which would be the same as -8 plus 8, which is 0. And so all three of these terms become 0, right? 0 minus 0 is 0, 0 minus 0 again is 0, and then -8 plus 8 is 0. So our x, y, and z component for this vector is 0, which means that the cross product of a vector with itself is equal to the 0 vector, the vector where all three components are 0. All right, and so that is the answer to this cross product. And you can use that as a fact from here on out. If you're ever asked to find the cross product between a vector and itself, you can just immediately assume that that is equal to the 0 vector. There's no other answer it could be because all of those terms are just going to cancel out and be 0. Okay, and so that's what I was talking about earlier with this being a property of the cross product. One of the properties of the cross product is that the cross product of a vector with itself will always be the 0 vector. Okay, let's take a look at a different example. All right, so next up we have this example. We want to find a unit vector that is orthogonal to both vector w and vector z. And we have that vector w is equal to the position vector of the point 4, -3, 1, and vector z is a position vector of the point 2, 5, 3. All right, so this is a little bit of a different problem, but it still involves the cross product. And how do I know that? Well, when you're asked to find a vector, let alone a unit vector, that is orthogonal to two other vectors, you are definitely going to be looking at a cross product. All right, because the definition of the vector that results from a cross product is a vector that is orthogonal to both of the vectors involved in that cross product. Okay, so if we want to find a unit vector that is orthogonal to both of these two vectors, we first need to find the cross product of those two vectors, because that's going to give us a vector that is orthogonal to both of them. Then we just need to find a unit vector from that vector. Okay, so let's start with that. Let's find the cross product of vector w and vector z. So we're going to have vector w cross vector z, and let's set up our 3x3 determinant here, or matrix. In the first row, we're going to have vector I, j, and k, our standard unit vectors. And then the second row will be the components of vector w, since that one is first. And then the third row will be the components of vector z, since that one is last. Okay, so we'll have 4, -3, 1, and then 2, 5, 3. All right, now let's calculate the determinant for this matrix that will give us our cross product. This will be equal to the determinant of the matrix after we cross out the row and the column for vector I. So we're going to be working with these four values. -3 times 3 is -9. So we're going to have -9 minus 1 times 5, which is 5. And that will be multiplied by I. Then we will subtract. We always subtract that second term that we're multiplying by j. and that determinant will be calculated from the values left over after we cross out the row and the column of vector j. So we're going to be working with these 4 values here. We'll have 4 times 3 minus 1 times 2. 4 times 3 is 12, so we have 12 minus 1 times 2, which is 2, and that's multiplied by j, and then we'll add that to one more term involving vector k. So if we go back to our matrix, we'll cross out this row and this column involving vector k, and then these 4 values are what we're going to use for the determinant. So we'll have 4 times 5 minus negative 3 times 2. 4 times 5 is 20, so we'll have 20 minus negative 3 times 2, which is negative 6. Okay, now if we simplify, this will be equal to negative 9 minus 5 times I. That will be negative 14i. And then we have minus 12 minus 2 times j. That will be 10j, but then we're subtracting it. So we have minus 10j. And then finally, we have plus 20 minus negative 6 times k. 20 minus negative 6 is the same as 20 plus 6. So we have 26 times k. So I'll write plus 26k. All right, so what we have here is the cross product of vector w and vector z. It is a vector that is orthogonal to both vector w and vector z, but it is not a unit vector. So now what we have to do is find a unit vector in the same direction as this vector. And so this goes back a little bit from earlier in Calculus 3 when we talked about finding unit vectors in the direction of a position vector. Remember that we can find a unit vector by taking a vector and dividing it by its magnitude. Okay, so in this case, our unit vector is going to be equal to vector w cross vector z divided by the magnitude of vector w cross vector z. All right, so all we have to do here to find the unit vector that is orthogonal to both vector w and vector z is take this cross product of vector w and vector z and divide it by its own magnitude. And so first of all, we need to find the magnitude of this vector. So let's do that. The magnitude of vector w cross vector z will be equal to the square root of the sum of the components squared. So we'll have negative 14 squared plus negative 10 squared plus 26 squared. Now negative 14 squared is 196. So this is equal to the square root of 196 plus negative 10 squared, which is 100, plus 26 squared, which is 676. Now 196 plus 100 is 296, plus 676 is 972. So if we continue our work up here, this is equal to the square root of 972, which we can simplify a little bit to make it easier to work with. 972 does have a factor that is a perfect square. It's equal to 324 times 3. So this would be equal to the square root of 324 times 3, and 324 is 18 squared. So if we take the square root of each part, we're left with 18 times the square root of 3. Okay, so that is the result, or the magnitude of this cross product. Now what we want to do is take the cross product of vector w and vector z and divide it by that magnitude to get our unit vector. All right, so here's what we'll have. Our unit vector that is orthogonal to both vector w and vector z will be equal to this vector divided by this magnitude, which will be the same as taking 1 divided by that magnitude and multiplying it by this vector. All right, so we're going to be multiplying that by negative 14i minus 10j plus 26k. And so if we do that, if we distribute this value through this quantity and multiply it by each of these terms, we will find that the unit vector is equal to negative 14 divided by 18 square roots of 3 times I minus 10 divided by 18 square roots of 3 times j plus 26 divided by 18 times the square root of 3 times k. All right, now you could leave it in this form, I guess, if you wanted to, but we can reduce each of these components by a factor of 2, right? 14 and 18 are both divisible by 2, 10 and 18 are both divisible by 2, and 26 and 18 are both divisible by 2. So if you reduce the coefficients of I, j, and k, or the components of the vector is what I mean, then you'll have that the unit vector is equal to negative 7 divided by 9 square roots of 3 times I minus 5 divided by 9 square roots of 3 times j plus 13 divided by 9 square roots of 3 times k. And that right there is the unit vector that is orthogonal to both vector w and vector z. We found the cross product of those vectors to get a vector that is orthogonal to both of them, and then found the unit vector in the direction of that vector. Let's take a look at another example. Hey there, real quick, before we take a look at the next example, if you find my tutorial videos here at JK Math to be helpful and you want access to more content such as exclusive bonus videos and dark mode versions of my videos, I'd invite you to check out my membership site JK Math Plus, where all of that content is available. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the video and take a look at the next example. Okay, so next up we want to find the cross product of vector v and vector u, and then show that it is orthogonal to both vector v and vector u. Now vector v is equal to negative 10i plus 6k, and vector u is equal to 5i minus 3j. All right, now we already know that the cross product of two vectors gives us a vector that is orthogonal to both of the vectors involved in that cross product. However, in this example, we are asked to also show or prove that that is true, that that cross product vector actually is orthogonal to both of these vectors. And we'll talk about how to show that that's true in just a little bit, but first, let's just find that cross product, and then we'll worry about that second part of showing that it is orthogonal to v and u. And so let's do that. Let's set up this cross product. We'll have vector v cross vector u, and that's going to be equal to the determinant of a 3x3 matrix, where we have our standard unit vectors, I, j, and k, and then the components of vector v in the second row, and the components of vector u in the third row. Now the components of vector v are negative 10, 0, and then 6, right? In this case, vector v doesn't have a term with j, so we can assume that the coefficient of j is 0. So the y component would be 0. So we'll have negative 10, 0, and then 6. All right, now for vector u, we have 5, negative 3, and then no term with k, so we can assume that the k coefficient is 0, or in other words, that the z component is 0. So we'll have 5, negative 3, and 0. All right, now let's calculate the cross product here. We'll start by looking at vector I here. We'll cross out this row and this column, and then calculate the 2x2 determinant here. We'll have 0 times 0 minus 6 times negative 3. So this will be equal to 0 minus negative 18, right? 0 times 0 is 0, and 6 times negative 3 is negative 18. That will be multiplied by I. Then we're subtracting that second term, which is multiplied by j, and then we're adding a third term multiplied by k. All right, now let's work on this term for j. We're going to cross out the row and the column for vector j and work with these four values here. We'll have negative 10 times 0 and then subtract 6 times 5. And negative 10 times 0 is 0 and 6 times 5 is 30. So we'll have 0 minus 30. And then for this last component, we will look at vector k. We'll cover up the row and the column for vector k and then work with the remaining four values. So we'll have negative 10 times negative 3, which is positive 30, minus 0 times 5, which is 0. So we have 30 minus 0. Okay, so now if we simplify, 0 minus negative 18 will be the same as 0 plus 18. So this is equal to 18i, and then we have minus 0 minus 30j. That will be negative 30j, but then that negative out front will make that negative 30 positive 30. So we have plus 30j, and then we're adding that to 30k, right? 30 minus 0 is 0, so we have plus 30k. All right, so that answers the first part of this problem. We found the cross product of vector v and vector u. It's the vector 18i plus 30j plus 30k. But now what we want to do is prove or show that this vector is orthogonal to both vector v and vector u. And the way that we can do this is by using the dot product. All right, so now you got to make sure that you know the difference between the dot product and the cross product. But before we talk about that, why do we want to use the dot product? Well, when the dot product of two vectors is 0, what does that tell us about those two vectors? It tells us that they are perpendicular, or that they're orthogonal, which is exactly what we want to show here, right? We want to show that this vector is orthogonal to vector v and vector u. So what we need to do is show that the dot product of this vector and vector v is equal to 0, and that the dot product of this vector and vector u is equal to 0. If those two dot products are both equal to 0, then we can conclude that this vector is indeed orthogonal or perpendicular to both of those vectors. Okay, so let's do that. We're going to take vector v cross vector u, and we're going to dot product that with vector v, and then we're going to do the same thing, except we're going to dot product with vector u instead. All right, so we're going to be multiplying by vector u. Now, in order to take a dot product, remember that it's equal to the sum of the product of corresponding components. So we're going to be multiplying the components of our cross product by the components of vector v for this first one. We'll multiply the x components together, then add that to multiplying the y components together, and then add that to multiplying the z components together. So we'll have 18 times negative 10. Those are our x components. And 18 times negative 10 is negative 180. Then we'll add that to our y components multiplied together, which will be 30 times 0, right? There is no j term, so the coefficient of j is 0, which means the y component is 0. So we have 0 times 30, which is 0. So we're adding 0, and then we add that to the product of our z components, which are 30 and 6. And 30 times 6 is 180. And so if you look at that, we have negative 180 plus 0, doesn't change the value, but then adding 180 will give us 0. So that checks out. The dot product of vector v and this cross product is 0, so we know for a fact that those two vectors are orthogonal. They're perpendicular. But now what about vector u and our cross product? We'll start by multiplying the x components. 18 times 5 is equal to 90. So we'll have 90 plus the product of the y components. So we'll have 30 times negative 3. 30 times negative 3 is negative 90. So we have negative 90, and then we're adding that to the product of the z components. So we have 30 times 0, right? We have no k term. The coefficient of k is therefore 0, which means the z component is 0. And so 0 times 30 is 0. So we're adding 0, which means that we have 90 plus negative 90 plus 0, which will be 0. So once again, we have now just shown that the dot product of vector u and this cross product vector is 0, so therefore they must be orthogonal or perpendicular. Okay, and so with that, we have now done everything that this problem wanted us to do. We found the cross product of vector v and vector u and showed that that vector is orthogonal to both v and u. We did that right here. Okay, let's take a look at a different example. All right, so next up we want to find two vectors that are orthogonal to both vector c and vector d. Now vector c is equal to 7i plus 3j plus 2k, and vector d is equal to I minus j plus 5k. All right, now if you watched all the other examples in this video, then you probably know exactly what you need to do to solve this problem. If you want to find two vectors that are orthogonal to both vector c and vector d, all that's asking you to do is to take the cross product of vector c and vector d, and then the cross product of vector d and vector c, the reverse order of that. However, we really only need to do the cross product once, because we know that if you reverse the order of a cross product, the resulting vector is the same vector, but negated. All right, so here's what I mean by that. All we have to do here is find the cross product of vector c and vector d, and then use that to find the cross product of vector d and vector c, because that is just going to be equal to the negative version of vector c cross vector d. We talked about this briefly in the second example in this video, that if you reverse the order of the cross product, you're just going to get the same vector, but in the opposite direction, meaning all of its components have the opposite signs. All right, so we only need to calculate the cross product once. We don't have to go through all of that work multiple times, just one time. And once we do that, we will be able to find both vectors. okay? Because remember, the cross product of two vectors will give us a vector that is orthogonal to both vectors involved. And so if we want two of them, which is the most that you can have, you're not going to be able to find more than two, then all you have to do is find the reverse of that cross product as well. Okay, so C cross D and D cross C are the only two vectors that meet these requirements of being orthogonal to both C and D. So those are the two vectors that we have to find. So let's find the cross product of C and D. Let's set up our matrix. We're going to have vector I, J, and K, and then the components of vector C, followed by the components of vector D. So I have 7, 3, and 2, and then 1, -1, and 5. All right, so 7, 3, 2, and then 1, -1, and 5. So now let's perform our cross product here. Let's find the 3 by 3 determinant. We'll start by looking at vector I. We'll cross out the row and the column that it's located in, and then use these four values to find a 2 by 2 determinant. 3 times 5 is 15, and then we're subtracting 2 times -1, which is -2. So we have 15 minus -2 times I. Then we're subtracting a term multiplied by j, and then adding a term multiplied by k. All right, now for j, we will be crossing out this row and this column and working with these four values. 7 times 5 is 35, and then we're subtracting 2 times 1, which is 2. So we have 35 minus 2. And then finally, for this term, for vector k, we will cross out the row and the column for vector k and work with these four values. So we'll have 7 times -1, which is -7, minus 3 times 1, which is 3. So we have -7 minus 3. All right, now if we simplify, this will be equal to 15 minus -2 times I. 15 minus -2 is the same as 15 plus 2, so that's 17. So we have 17I minus 35 minus 2 times j. 35 minus 2 is 33, so we will have 33j, or -33j, because we're subtracting that term. And then we're adding that to -7 minus 3 times k, and -7 minus 3 is a -10, so we will have minus 10 times k. So let me erase that plus sign, because instead we're going to have minus 10k. All right, and so that right there is the cross product of vector C and vector D. That is one vector that is orthogonal to both vector C and vector D, 17i minus 33j minus 10k. But then if we want to find a second vector that's orthogonal to both of those vectors, this is number 1, our second one will be the same as this vector, but where each component is negated. That will be D cross C. We'll take -1 and multiply it by this vector. And so if we do that, we will get the following vector of -17i plus 33j plus 10k, right? We just reversed each of those signs. So 17 became -17, -33 became +33, and -10 became +10, all right? And so that is the second vector that is orthogonal to both C and D. And there are no more after that. That's it. Okay? Let's take a look at one more example for this video. Okay, so here's our last example. We have if the magnitude of vector v is equal to 9, the magnitude of vector w is equal to 2, the angle between vector v and vector w is pi divided by 6 radians, and the direction of vector v cross vector w, or the cross product of those two vectors, is described by the unit vector vector u is equal to 2i minus 2j plus k, then find that cross product. All right, so this is very different from all of our previous examples because this is going to involve a different formula for the cross product, or a different way of finding the cross product. I show you where this formula comes from in my lesson video, so be sure to check that out if you haven't already. And the formula looks like this. I like to call it the alternate form of the cross product because we also have an alternate form of the dot product, so why don't we just call this the alternate form of the cross product. But anyway, another way to find the cross product between two vectors is to take each of their magnitudes, multiply them together, and then multiply them by sine of theta, where theta is the angle between those two vectors, and then you multiply by a unit vector that describes the direction of that cross product. Now in this case, we have everything we need to find this cross product. So really this problem is just kind of one of those plug and chug problems where you just plug in everything that you know and get the resulting answer. Okay, but it is important that you can identify all of the different parts of this problem and how they relate to this formula. All right, because what we're going to have in this case is the cross product of vector v and vector w, and that's going to be equal to the magnitude of vector v times the magnitude of vector w times sine of the angle between those two vectors times a unit vector describing the direction of that cross product. Okay, so I just modeled this equation after this formula right here. And so now let's identify everything we know and then plug in our values and get our answer. We already know that the magnitude of vector v is 9 and the magnitude of vector w is 2, so we don't really need to write those down again. In fact, we can just plug those into this formula. We'll have that this is equal to 9 times 2, and then we're multiplying by sine of theta, where theta is the angle between vector v and vector w. And we're told what that is. We were told that the angle between vector v and vector w is pi divided by 6 radians. All right, so that angle is theta. Theta is equal to pi divided by 6 radians. So let's plug that in here. We'll have pi divided by 6. And then we're multiplying all of that by a unit vector that describes the direction of the cross product, which in this case we are given. The direction of this cross product is described by the unit vector right here, 2i minus 2j plus k. So let's write that in here. We'll have 2i minus 2j plus k. Okay, so now all that's left to do is simplify. So let's do that. 9 times 2 is 18. So this is equal to 18 times sine of pi divided by 6. You might have that memorized and know that it's 1/2, but if not, just plug it in your calculator. Sine of pi divided by 6 is 1/2, and then we're still multiplying that by this unit vector. So write that down again. 2i minus 2j plus k. 18 times 1/2 is 9, so now we're just going to be multiplying 9 by each of these components, or each of these terms. And so our final answer is that this cross product will be equal to 18i minus 18j plus 9k, right? 18 times 1/2 is 9, like we said, and then 9 times 2i is 18i, 9 times negative 2j is negative 18j, and then 9 times k is 9k. And so that right there is the cross product of vector v and vector w using the magnitudes of those vectors, the angle between them, and the direction of that cross product. Okay, and so with that, this was the last example for this video, but if you do want to see some more examples related to the cross product, I do have a couple more available on my membership site, so if that is something that interests you, feel free to look into becoming a member. If you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.